My camera ran out of power, so this will be another part of structural geology, investigating the characteristics of cracks, fractures, stress, strain, and the like. The information I am summarizing and reducing in length from the over 4-hour lecture by Kathina Gunn-Rosas. Continuing on. The Plumo Structure. This occurs on the fracture facies or joints. It represents the propagation of stress along the joint as it forms. Joints are formed by tensile stress, a load 1 loading. No rock is homogeneous or completely, and the forces on it are not isotropic, same in every direction. So we will see irregularities in the homogeneous, non-isotropic rock. Isotropic means that the forces in a rock are different in different directions. Surface morphology, continuing. And we are almost done. Now, when you enter the mist zone, you have less smooth fractures becoming imperfect due to imperfections encountered by the stress. In the Hackle Zone, which is the main region, it is rough. These cracks or lines represent the Hackle Zone. There are barbs curving departure arms from the main structure whose acute angle with the main line fracture path or plumose axis point toward the origin. Imperfections are due to different stresses. Promulgation, direction. These are the stresses on the Plumo structure. The orientation of the stresses. Other times, you'll see fractures which light up at something called arrest lines. Then these fractures, which is a reduction of stress, but the stress continues until the next arrest line, and the cycle continues. Many times we will see arrest lines in a material because it takes certain amount of stress to achieve this, and some stress is relieved when there is a break in the rock. But stress is usually accumulating, so at some time the stress is reactivated and it keeps on promulgating. This is called a cycle. That is, the surface morphology of the fracture planes along the joints. You can read the stress history. You can deduce what happens in this morphology in history past. There are different types of joints. Some joint sets are set up in horizontal and vertical lines. They are called orthogonal joints. Others resemble triangles and are called conjugate joints. And others resemble hexagons. Not necessarily all 6 sides, some have 5. And they are called columnar joints. They are systems of joints. Systematic joints are planar and have spacing and parallel to subparallel distribution. Non-systematic joints tend to be non-planar and have no such relationship to each other. They often terminate at other joints. Joint sets behave in a similar way, or are parallel or subparallel and have a relation to each other that is quantifiable. Joint systems are made up of two or more joint sets that have the same quantifiable relationship to each other. Master joints, which are long joints and continuous, move all the way through the bed. Cross joints terminate at the master joints. After all, a joint cannot cross a free surface, and a master joint is a free surface. Cross joints do not cross the master joints because master joints act as free surfaces, and our small cross joints can't propagate across them. Systematic joints tend to be planar. Non-systematic tend to be non-planar and don't have the same parallel or subparallel relationships that systematic joints have. They also terminate in larger joints. With sills and dikes that intrude in a shallow crust, as they freeze, they experience cooling and contracting that creates tensile stress in the rock that is beginning to freeze and can no longer contract. Columnar jointing develops, in which the tensile stress is seen as it cools. They are curved joint sets. Igneous jointing is shallow still, and dike inclusions in igneous material often develop distinctive columnar jointing with long axes perpendicular to the boundaries of the intrusion, the horizontal in dikes and vertical in sills. They are cooling material, freezes and contracts. Cooling material freezes and contracts and forms joints. The non-hexagonal cross sections represent the distribution of tensile stresses. Magma inclusions that experience uplift expose an exfoliation of the overburden often show exfoliation, a distinctive jointing parallel to the rock content. Joint formation at different time. Hooking and sigmoidal joints occur when remote stresses and local stresses are oriented differently. And we can see these in these diagrams. Here we see an older joint C and an older joint B. Here's stress sigma 3. Here is the newer joint, and so it curves and forms a sigmoidal pattern. It is younger. In this case, we have an older joint B, which is continuous. We have a newer, younger, remote sigma 3 joint that in this case cannot cross the older joint B, but wants to terminate at a 90-degree angle, so it curves. That's called hooking at J junctions. A newly formed joint is usually going to have, it will be acted upon by the stress field of the older joint. Sigma joints form like this because, sigma joints formed like this pattern because they have a conform to the older joints. Joints usually form in response to tensile stress. The tensile stress on a bed will break open a joint, and then it will be relieved somewhat. But as you move away from that joint, the relief experience from that joint is going to taper off, A thinner bed is going to have less strength to resist the tensile stresses, and it will have closer spacing because of the stress shadow is very narrow. A stress shadow develops around a joint. Joints cannot cross into each other's stress shadow and therefore stop. So a thinner bed will have narrower spacing between joints. The lithology of the bed will decide the Young's modulus. Also, the stress field affects distance between joints. With more stress, the narrower the spacing between joints. From that, we can quantify the history of the rock. So why study joints in the field? Well, for engineering and hydraulic applications, water fills the joints and can become a what's called below the water line, an aquifer. Foundation strength. We study joints for foundation strength to build buildings. Mining and quarrying operational feasibility. Groundwater and aquifer properties. And toxic waste safety risk. If a toxic site is near a land that has many joints, those joints can carry liquid from the toxic waste dump, the toxic fluid in the joints, and that is a bad situation. Academic issues include historical stresses, historical orientations, regional tectonic and event history, regional emplacement events, igneous modifying history, and lithological properties and their relationships to developing joints. My camera has run out of memory, and so we will continue this on another part. Again, I'm reading fast to shorten her video. So go back and review sections that you didn't understand, and then continue on. And until the next time, this is Frank with Frank's Beautiful Rocks and Minerals, always reminding you to keep looking down. Next, we'll start with brittle deformation. Selected joint genesis.